So now let's take some of the problem which is based on properties of pure substance. So first I am writing the problem first, and then we will discuss about this problem. So in that problem, find the saturation temperature, the changes in specific volume, and entropy during evaporation, evaporation, and the and the latent heat of vaporization of steam at 1 megapascal. I'm just repeating the problem again. Find the saturation temperature, the changes in specific volume and entropy during vaporization, and the latent heat of vaporization of steam at 1 megapascal. So now we will solve this problem. For this problem in GATE they will give the table, but for our understanding I will take the properties from the steam table. So in steam table I am just looking at 1 megapascal. What are the things available? If we look in steam table at 1 megapascal, we will get T saturation. It is 179.91 degrees centigrade. You can take volume, specific volume, it is not volume, specific volume of liquid, that is 0.001127 meter cube per kg. You can also refer your steam table for your understanding. Specific volume of vapor will be 0.19444 meter cube per kg. And now we are interested in change in specific volume entropy during vaporization. So vaporization is nothing but we can say that it's a process where the phase is changing. So the latent heat will come into the play. For latent heat, what we have to do? We have to subtract the properties of vapor with properties of liquid. So suppose we want specific volume, that is for VFG. So we have to put Vg minus Vf, specific volume vapor minus specific volume of liquid. So that is we will get 0.1933 meter cube per kg. Similarly, by table we are having entropy of liquid, that is 2.1387 kilojoule per kg Kelvin. Similarly, the entropy of vapor is 6.5865 kilojoule per kg Kelvin. And now for this change in entropy during vaporization, we are having SFG equals to Sg minus Sf. We'll get 4.4478 kilojoule per kg Kelvin. Similarly, we can get change in enthalpy during evaporation, that is HFG. We can write Hg minus Hf, and we are having with the table 2015.3 kilojoule per kg. So by this way we can easily find out the change in specific volume entropy during the phase change. Now I am taking another very important problem for understanding the fundamentals of properties of pure substance. So first I will write the problem. A vessel of volume 0.04 meter cube contains a mixture of contains a mixture of saturated water, saturated water, and saturated steam and saturated steam at a temperature of 250 degrees centigrade, 250 degrees centigrade, contains a mixture of contains a mixture of mixture of okay, I am again repeating, sorry. A vessel of volume 0.04 meter cube contains a mixture of saturated water and saturated steam at a temperature of 250 degrees centigrade, 250 degrees centigrade. The mass of the liquid, the mass of the liquid present is 9 kg, present is 9 kg. Now we have to find the pressure, mass, mass, the specific volume, enthalpy, entropy, and the internal energy. Internal energy. So I will again repeat the problem. A vessel of volume 0.04 meter cube is given, which is containing a mixture of saturated water and saturated steam at a temperature of 250 degrees centigrade. The mass of the liquid present is 9 kg. Find the pressure, mass, specific volume, enthalpy, entropy, and internal energy. Now let's start the solution of problem. Solution. So here also, if I mention, if this kind of question they will ask in GATE examination, so they will give the table or directly they will give the values. But right now I am taking the required values from the steam table. So I will write from steam table at 250 degrees centigrade we are having saturation pressure that is 3.973 megapascal. Vf, that is specific volume of liquid, that is 0.0012512 meter cube by kg from steam table. Specific volume of vapor 0.05013 meter cube by kg. So enthalpy or specific enthalpy, because whatever value I am writing, it is with respect to per unit mass. So the specific enthalpy of liquid, that is 1085.36 kilojoule per kg, and that is latent enthalpy of the mixture, that is 1716.2 kilojoule per kg. Similarly, the entropy of liquid is 2.7927 kilojoule per kg Kelvin, and the difference in the entropy, that is SFG, is nothing but Sg minus Sf, is 3.2802 kilojoule per kg Kelvin. So now we have already taken values from the steam table, and now easily we can plug. In the problem, the mass of the liquid is given. So mass of liquid is given, that is then denoted by mf is given, that is 9 kg. So now I can find out the volume of liquid. So volume of liquid I will define by capital PF. So volume of liquid MF into specific volume, that is VF. So here I will write small v for better understanding. So now MF we know 9 kg. VF from data here we are having this value. I will plug here 0.0012512. If we multiplied it, we will get 0.01126 meter cube. That is volume of the liquid. Similarly, we are right now we are having the volume of the liquid, and we are having the vessel which is having a volume of 0.04. So 0.04 is the volume of, we can say that, mixture. So now we can find out easily the volume of vapor. So the volume of vapor, that is Vg, we can find out. We are having the total volume, that is 0.04. If we subtract the volume of liquid, that is 0.01126, so we will get the volume of the vapor, that is 0.02874 meter. Now we can easily get the mass of the vapor. So mass of vapor you can easily find out, because mass of the liquids we are having mass of the vapor, let's say that mg. Here you can find out that is volume of the vapor divided by specific volume of the vapor. So volume of the vapor we are in 0.02874, and the specific volume we are having in the table, that is Vg, was to 0.05013. So the mass of the vapor we will get 0.575 kg. So now we are having the mass of the vapor, we are having the mass of the liquid, so we can get the mass of the mixture. So the mass of mixture was to M equals to MF plus Mg. So mass MF is nothing but 9, Mg is 0.575. So the mass of the mixture will be 9.575 kg. Now we can easily calculate the quality of mixture, because we are having mass of mixture and we are having mass of vapor. So now we will define quality of mixture, that is X, and we know X is a Danish fraction defined with mg, mass of the vapor, and mass of the liquid plus mass of the vapor. So here we can define X equals to, we are having mass of the vapor, that is 0.575, and mass of the mixture we have already calculated 9.575. So we are having 0.06. So the dryness fraction or quality of the mixture is 0.06. Now we can easily calculate the specific volume of mixture by formulas which is used for liquid vapor mixture. So we know specific volume of mixture will be specific volume of liquid plus X, and difference in specific volume of liquid and gas, liquid and we can say that vapor. So now we are having, we have already calculated, that is 0.4 we have already got from the steam table, 0.0012512 plus X we have already calculated 0.06. It is nothing but Vg minus Vf. It is nothing but Vg minus Vf. So here again I will write 0.0012512 plus 0.06. Vg we are having the value 0.05013 from the steam table. Vf we are having a specific volume of liquid 0.0012512, and if we calculate this specific volume of mixture, it will come 0.00418 meter cube kg. That is the specific volume of the mixture. Similarly, specific enthalpy of the mixture, we can calculate H equals to HF plus XHG, or we can write H equals to HF plus XHG minus H. From steam table, we are having the value of HF, that is 1085.36. We are having the value of X, we already calculated the inspection, 0.06 into difference in that 1716.2. So from here we can easily calculate specific enthalpy of the mixture, 1188.32 kilojoule per kg. Now we can calculate the specific entropy of the mixture. We have formula S equals to SF plus X Sg minus Sf. Now Sf, we know the value of Sf is 2.7927 plus X is 0.06, and the difference is given in the problem, that is nothing but Sfg. So S equals to 2.7927 plus 0.06 into Sfg is 3.2802, and if you calculate this thing, you will get the specific enthalpy of the mixture, that is 2.9895 kilojoule per kg. So this one is the specific enthalpy of the mixture. Now let's take the specific internal energy. So specific internal energy is U, and if we know the formula in terms of enthalpy and PV, it is H minus PV. So U we can already calculate. I will say small u because I am taking specific enthalpy. H, we are having this thing, that is 1188.32, we have already calculated. P, we are having this value 3.973 into 10 to the power 3, that is pressure. And volume, specific volume of the mixture, we have already calculated, it is 0.00418. It is the specific volume of the mixture, Now if we calculate this specific internal energy, it will come 1171.72 kilojoule per kg. So this one is the specific internal energy of the mixture. Now we can also calculate this specific internal energy of the mixture by some other method. It is suppose at 250 degrees centigrade we are having specific internal energy of liquid is 1080.39, this kilojoule per kg. Similarly, we are having the difference of specific internal energy of liquid and vapor, that is 1522.0 kilojoule per kg. And now we apply the formula for mixture. U, that is specific enthalpy of mixture, equals to UF plus XUG. And if we put the value here, UF is 108039 plus X 0.06 into UFG, that is 1522. So we can easily get the specific enthalpy of the mixture, 1071.71 kilojoule per kg. So by this way we can easily calculate it, and if you see both the values are same. So now we can calculate the different properties of the mixtures, liquid vapor mixture, with the help of general mixture formulas. Now let's take a very good problem which is based on properties of pure substance as well as steady flow energy equation. So first I am writing the problem. It's very important problem for understanding the fundamentals. So I am just writing the problem first. Steam initially at 1.5 megapascal, 300 degrees centigrade, expands reversibly and adiabatically adiabatically in a steam turbine steam turbine to 40 degrees centigrade. Here I will explain one thing. We mentioned that is reversibly and adiabatic. So reversible adiabatic process is isentropic process. So remember one thing. Whenever I will say adiabatic, so adiabatic is not a isentropic process, but if I say adiabatic reversible process, then it is isentropic process. Means in this process, entropy of the system will be the same, means entropy of the system will remain constant. So in this problem, determine the ideal work output of the turbine per kg of steam per kg of steam. Whenever we are talking about the quantity per kg, then it's a specific quantity. So basically we are interested in specific work done. So now I am solving the problem. For this problem, if we apply the steady flow energy equation. So first of all, I will just draw the diagram. What is the turbine here? This one is the diagram for the turbine. Here we are having steam which is initially at 1.5 megapascal and 300 degrees centigrade, and here I am doing the steam that is at 40 degrees. So let's take this one is section 1 and this one is section 2, and now there is a work output, the shaft work, and suppose now I am applying the steady flow energy equation. So steady flow energy equation. And according to the steady flow energy equation, I can write Q plus H1 is V1 square by 2 plus GH1 equals to W plus H2 plus V2 square by 2 plus GH2. It is in a horizontal position. So in this problem, so the expansion is reversible adiabatic. Adiabatic means no heat exchange between systems. Q is 0. It is a horizontal device, so potential energy at inlet and outlet will be same. Ultimately, we are saying it's the same, GH1 plus 2 GH2. Or suppose I am neglecting the other energy terms, and I am also neglecting the kinetic energy. So if I write again, then we get H1 plus 2 W plus H2. So work done, I am having H1 minus H2. So by this way, I can calculate the work done H1 or work done with the help of H1 and H2. So now for this process, I am just drawing the TS and HS diagram. I'm just drawing TS diagram first. We know we already discussed like this way we can draw the TS. This one is the constant temperature lines here. And suppose I am having state here, that's 1. at 300 degrees centigrade, and this one is at 40 degrees centigrade. And if it is expanding here, I will get a point 2. That is in the dome, means one is in superheated state, and two, it is in liquid vapor mixture form. So here at point 2, we have to find out the dryness fraction value. Then only we can calculate enthalpy at point 2. Similarly, we can also draw this thing on enthalpy entropy diagram. We know this one is the enthalpy entropy diagram, and this one is the temperature lines here. If you see here, we are here, and if we are going 1 to 2 again, 2 is in 4. This is 300 degrees centigrade, this is 40 degrees centigrade. So this is in liquid vapor mixture state. So from steam table, I can write at 40 degrees centigrade we are having P saturation is 7.384 kilopascal. Entropy of liquid, it is specific entropy, 0.5725 kilojoule per kg Kelvin. Specific entropy or specific entropy difference between means vapor and liquid is 7.6845 kilojoule per kg Kelvin. Enthalpy of liquid, specific enthalpy, that is 167.57 kilojoule per kg. Specific enthalpy difference between vapor and liquid, that is 2406.7 kilojoule per kg. Now at P equals to 1.5 megapascal, T equals to 300 degrees centigrade, we are having S1, that is in superheated steam. So directly I am considering specific entropy at state 1, that is 6.919 kilojoule per kg. H1 is 3037.6 kilojoule per kg. If you see the diagram here, if you see the diagram here, so we are having 1 and 2. We are having two things, 1 and 2. If you see 1 and 2, entropy at 1 is equals to entropy at 2. So I can write S1 is to S2. I can write here S1 equals to S2. So now I am having the value of S1, that is 6.9189, and for S2 I can write SF plus X2 SG, that is at 40 degrees centigrade, or I can write at 40 degrees centigrade. 6.9189 SF at 40 degrees centigrade, we know that is 0.5725. X2 we have to calculate. SFG we are having 7.6845. So X2 will be 6.3464 divided by 7.6845 equals to 0.826, or we can say that 82.6%. Now we are having the value of X2 here, that is quality of steam at point 2. So with the help of quality of steam at point 2, we can find out specific enthalpy at point 2. So now calculate the specific enthalpy at point 2. H2 equals to HF 40 degrees centigrade plus x2 HFG at 40 degrees centigrade. So we are having the value here HF at 40 degrees centigrade, that is 167.57. X2 we have already calculated, that is 0.826, and HFG at 40 degrees centigrade 2406.7. So by this way we can calculate the value of H2, that is 2152.57 kilojoule per kg, and if we put in work done, that is H1 minus H2, we can get the value of specific work, that is work done per unit mass. So H1 we already know 3037.6, H2 we calculated 2152.57. So work done is nothing but 885.03 kilojoule. So by this way we can easily find out the specific work done.